This is Bill Bright with Gallup Solar, and this is Solar101 Electric Current. I'm tag teaming tonight with Pam Maples. We haven't seen either one of our presentations, and that's on purpose so that we don't, we have a completely different approach to life anyway, and I'm going to bore you with some lecture, so to speak, not too boring, hopefully. And I understand Pam, last I heard, was going to beat you over the head with a water hose or something like that. But either way, hopefully by the end of the hour, I'm going to try to keep mine to 30 minutes, that you'll really have an appreciation for electric current. This is most important for understanding photovoltaics and solar panels because it's the basis. And as I will try to emphasize tonight, it's really the basis of life itself. So with that, I want to go ahead and introduce the concept with a few slides, very simple. And this is how solar electric current works. Any questions? You said we had the challenge of making it very simple. And so I picked this glyph from the internet to basically get down to the root cause, and they have to do with atoms. I know none of you have seen these things. I hope that everybody here is okay with accepting the possibility that all life is made up of little tiny particles inside of us and outside of us in the whole universe, atoms. And these particles, we do have a kind of a preview of it, I think. I'd like to think of it. And that's the solar system. Our sun is the nucleus there, and those electrons going by are our planets. So to me it gives you kind of an interesting macro view of something we can't see in the microcosm. But basically this is it. Imagine these electrons being, of course, many, many, many millions and zillions in a small place, in a wire or in our body or whatever. And that little electron moving from one energy spot to another is basically current. And it adds up, if you get so many of them, it adds up to a potential amount, whether it's in our body or whether it's lightning, which we see quite a bit of around here. And really that's all there is to it. I did pick two different types of atoms here. One has a different number of electrons than the other, but there's no particular designation here as to what element they might be. But this is important to remember for a later lesson, because when we study how PV works, we'll see this again, that there's two different elements in the periodic table that are side by side with the barrier between them, and the sun causing this flow. So you'll see more of this later in a later presentation. So that's the basis of what we're talking about. Now, it just turns out that in the 1800s, when the science was really getting started, there's all kinds of excitement and experimentation and wonder and wonderful thoughts coming about having to do with electric current. And it's not that long ago that people just didn't have any idea. And it just turns out this is an international experiment. And in France, there was a man, last name AMPERES, who was given credit arbitrarily by the scientific community at that time for the concept of a certain amount of electric current. There's actually another person, Coulombs, I believe he's French also, that actually came up with a number of how many gazillion electrons moving through a particular space creates 1 amp. Amp is short for amperes. And I don't know, don't ask me how I figured that out, but we don't need to worry about that. It's an arbitrary measure of a certain electric flow. It's important when we get to sizing our PV panels that we understand this concept of an amp being a certain flow of electrons from the atoms. Now, you might ask, why are the electrons flowing from one to another? And that would be the next example. And from there, got this in the wrong order here. From there, we have to fly to Italy, and then last name, another scientist working at the same time, last name Volta, has been giving credit to answering the question of why electrons flow. Well, there's a potential set up. Somehow, for various reasons, whether it's static electricity from lightning, whether it's chemistry in our body, photovoltaics, which they didn't know about at that time, something creates a potential, a charge, a negative and a positive. And you'll see these negative and positive later when we get into designing photovoltaic systems. They're an important concept. Various things can create a charge, basically a potential, something that makes these electrons want to move from one place to another. And without that, why would they move? So we need to understand that's quite simply, a volt. So now we have an amp, now we have a volt, and that begs another question. Why does it flow all the time? Why are some substances, copper wires, things flow better than other kinds of wires and materials? Why is there a difference in the flow of the amps when you have the same volt, in it? And that has to do with, we have to take another trip now to Germany. Last name, scientist, the same time period, last name OHMS. He's given credit to the idea, well, there's resistance, different amounts of resistance with different elements. And these two atoms are picked because they're very similar. There's not a whole lot of action going on. They have no reason. They're kind of holding up the idea of changing electrons. There's too much resistance. So it's that simple. Now we have three key concepts to remember. And what we have is Ohm's law. Now we have something that science can work with, and we will work with this in the later lessons on designing photovoltaic systems. We need to know this law and its relationships. And some people like to use this triangle as a way of remembering it. I remember seeing this. By the way, my introduction to electric current was courtesy of a free class for 1-year class in Denver, courtesy of the United States Air Force. And so I had a whole year of wonderful experience really in the classroom learning electric theory as well as a number of other things in the Air Force. So this relationship of Ohm's law is something we will actually utilize. This is a little bit of math, but it's something that we will need to have be able to do when we calculate size of wires, various things in our photovoltaic systems. Let's say we have a battery that's 1 volt in the first example, and we have a multimeter. Now that's another, I hope we'll have something on multimeters later. It's a simple little object that you can pick up very reasonably from any Radio Shack or anywhere else, and it'll measure volts, amps, and ohms. And so it's something we actually use in the field. It's very handy. So now we have this multimeter. We have a 1 volt battery through, let's say, some kind of wire, and we read that 1 amp of current is moving through that. All those electrons that somebody said is an amp is moving through there. Well, the law is, well, that must have 1 ohm of resistance. It's that simple. If 1 volt is hooked to a certain conductor and you read 1 amp, then automatically that's how they figure that must have 1 ohm. So from there, you can take a little bit of simple math here and say, well, we still have a 1 volt battery. We hook it up to a different kind of wire, let's say gold, and we get 2 amps flowing through there with our meter. So what happens? It must have only half an ohm. It's just simple math here, because it's conducting better. And that's true of various elements. They have different levels of resistance. Down here, the opposite is true. We still have the 1 volt battery. We only get a half an amp. It's some kind of metal that not very good at conducting, and you only get half an amp. Must be 2 ohms in that in that metal. And so maybe you wouldn't want to use that. This is critical later as we calculate the voltage drop between our photovoltaic panels going into the house with going through copper wires usually. And we need to be able to prove to the inspector that there won't be enough resistance and voltage drop to make that system, where the system won't work. The inverters, the battery chargers, and so on, they just won't, we have the voltage out there at the panels where we run through these wires and the thing doesn't work. Well, there was too much of a drop because we didn't have the right size wires, right size copper wires. So that, in essence, is what Ohm's law is about. Now, somewhere along a little later, in the early 1900s, we had a whole concept, and from here we're going to fly to Scotland. A man whose last name, sorry, these are all men. I'm sure women actually did all this, but the men get the credit, as usual. But this gentleman in Scotland, last name Watts, it was part of a whole movement to understand power. That was the time, we were looking at horsepower. You've heard about horsepower in your car, your vehicle. At that time, horses were providing all the power. And so there was an actual formula made based on how much a horse could pull to come up with the concept of horsepower. Well, same thing with electricity. To be able to calculate these things and figure out what kind of work they can do, we need to figure out what kind of power is inherent in electric current. So basically, this is easier math. 1 amp times 1 volt equals 1 watt. And that's basically something we can work with. You know about watts because you've all changed a light bulb and you've seen that there's so many watts, 60 watt, 100 watt. That's the idea, how much power they're going to need. And later on, as we calculate off-grid houses, basically we need to look at all the labels and the wattage of the various machines and devices. We've asked people to fill that on a form. How many hours are they using these wattage? Otherwise, how can we figure how many panels and how many batteries there are going to be so they don't run out of power every day? So that works, and that simple math works in much simpler ways. Let's say we have 1 amp and 2 volts. It's 2 watts. It's just a simple mathematical change. And what's interesting, it works the opposite, just the opposite. If we measure 2 amps at only 1 volt, it's still 2 watts. This is just multiplication. Amps times volts is watts. And then we can use watts as a concept when we calculate sizing later on. You'll appreciate this. Now, I want to emphasize there's some discussion and some healthy fear about electricity in our populations and our cultures of the area. And you've all heard the term that water is life. It's a wonderful expression, very true. But water, when it comes down the arroyo, can also be deadly. And same thing with electricity. I say that let's start the new concept tonight. Electricity really is life also, and just as important as water. You can live for several days without water, but I submit to you, you won't live for a few minutes without electricity. We have one member of our audience who has a pacemaker that he showed me last week, and without that extra jolt of electricity to his heart, it could be, life-saving. And we all have that pacemaker naturally within us, normally if it's working. And so our heart won't beat without that electric current telling the heart to beat and to pick up the beat when we exercise. So while you're watching this, the transmission of the visuals to your brain is going through neurons because of electricity. So I'd like to get everybody to embrace the concept that electric current is absolutely necessary for life. Nothing to be afraid of. We're not going to go out, stand outside during an electric storm, but I think, to really appreciate that electricity is inside of us and outside of us and everywhere.